Well, Gary, first of all, I use the term proof within physics, okay? There's no doubt that classical physics led to the Standard Model, which is now non-deterministic. So the big group of people you had saying that the universe was a mechanistic, deterministic thing, those theories, as they were advanced, turned into the Standard Model. They simply couldn't advance anymore. They ran up against the wall, and we saw where they were incomplete, okay? You can have another school. You can start another school of physics, a different way of looking at it. You can have a theological physics, but you can't go to the school of physics and say, "Hey, Newton can't be right because the four elements are fire, earth, water, and wind, and he didn't mention them." That was because that was physics too at one point. Okay, so that's what you can't do. Now, there's no way what I'm arguing for as weird as what you take. It's just you believe in certain principles that you just can't do without. The world makes no sense without those principles. Okay, I don't even think the issue really is randomness. I don't think quantumness says that things are random and it changes the way the pool ball goes. No, I mean, there's statistics. There's laws of statistics, and those are not only unchanged but become really important in quantum mechanics. And in the laws of statistics, with the trillions and trillions of particles involved in the bowling ball, you're going to have these statistical effects. The randomness of quantum is not going to affect it unless somebody builds a quantum, bowling ball or some special device. Ordinarily, you're going to have ordinary statistics in play. Things are going to play out. They're going to fill in these bell curves. And you can make predictions about that. And since we're in the macroscopic world always with billions and trillions of events, for every little thing that we see, no matter how small it is, it has millions of events associated with it, of these kinds of quantum events. And you're going to see the bell curve. You're going to perceive the pattern. Okay? And that's all that we're saying about proof. And I do not say there is no cause and effect, and I've been really clear about this, and you ought to understand this by now. I do not say that there's no cause and effect. I say we need a different version of cause and effect, and you seem to not like it. It doesn't suit your sensibilities. But the problem is your attempt to make a more common sense physics. I mean, there's a reason that has not succeeded so far. Lots of physicists also have wanted to do that. For example, the hidden variable theories. That's fine. David Bohm created a hidden variable theory. He rearranged the mathematics and said, look, there's a hidden variable theory. It's possible. Well, fine, except for one, you can't know the hidden variable still. Okay, so there's the epistemological question of things that are impossible to know, and what kind of knowledge is that really? But separate from that, given that, well, somebody might be able to know it, the theory still violates locality. The no spooky action at a distance, it violates that. So hidden variable theories sounds nice when you get to reclaim your realism, but it's not a very positivist view of the world because you still have things that are across the universe affecting each other. The hidden variable theories are just as weird as the quantum mechanical ones. And you guys criticize quantum mechanics too much. We're not taking all these interpretations that you've heard, these what the bleep do you know kind of interpretations. Physics, is not about touting those. They know they need to work on the interpretations, and they're actually very, very hesitant to make interpretations. Okay? But when you try to make interpretations that fit it, you end up with these weird theories. And holding on to classical mechanics makes them weirder, not less weird. It makes it even weirder. You have hidden variable theories. The photons are flying out of the screen towards the emitter. How are these any better if common sense is the rule? It's pretty clear that with quantum mechanics, we've reached a point of seeing the evidence. You say there's no evidence. There's shitloads of evidence, okay, that the mathematical model matches reality. Now, how do we interpret the meaning of why does that mathematical model apply? Well, then we're trying to get an interpretation that makes sense, that we can describe why that model applies, okay? And there are no simple ones. They all break our intuition. And we're just dumb apes, right? We're just bacteria with brains. So the fact that we have trouble formulating an accurate theory doesn't make the theory impossible. It's a reason to resist the theory, but we've been resisting this one for quite a while with some pretty great minds. And the issue is not about the randomness. It's not that, oh, we've seen randomness firsthand. This issue is this. The reason you can tell if an electron went through the window, through the slit, by throwing it, is you put a detector. So if you threw me at a slit and had a detector, you know, you just threw it, and sometimes I would hit the gap, and I'd go through and I'd hit the screen. And even though you couldn't see me, if you had a kind of screen that could see me, in other words, you could create an electronic eye that could see me, then you could indirectly see me. You might not know what I was. Maybe you couldn't know whether I was a monkey or a human, but you'd start to learn things, yeah, about my mass, about how I behaved in the world. The issue with the two-slit experiment is that you see interference patterns. So the concrete conclusion, the one that is most touted by quantum mechanics, is that the electron surprisingly behaves like a wave, which is odd because we knew already that it primarily behaves as a particle. But we can see that it behaves as a wave. We have no other metaphor of what it behaves as besides a wave. You can make one up, but the wave is pretty damn clear in that waves can go through two slits at once, because the wave front is a ripple, and it comes up, and when it hits that screen, it hits the whole screen at once. And the parts that hit the slits go through it and acts like little emitters, basically, because of diffraction. Waves fan out a little bit after going through a passage like that, and you have something that, you know, new little ripples. They're not the full circles, but they're part arcs, you know, and they propagate and they overlap, and we see that interference pattern. That does not happen with the particle idea. So that leads us to the question of what kind of field are they in? What is the wave in? What's the water of this wave, if we're using a water wave metaphor? What's the medium? All right. We don't know. But we do know that the peak of the medium, the peak of the wave in the medium, is the most likely particulate location for that particle to be. And we know that under the whole wave packet, there's 100% probability. Somewhere it's within this finite bounded wave packet. There's points in the wave packet that get to zero, it'll never be there. And there's other points where it's bigger or lower, and the whole volume adds up to 100% chance that it's somewhere in there. And that's just how it looks, you know. And it doesn't mean there's no cause and effect. It's not the randomness. Quantum mechanics doesn't say it, but quantum mechanics, you know, there's patterns. You would call them maybe deterministic or certain patterns, but I think that's the wrong way to call them. But there are definitely patterns that emerge in these things. And for example, conservation of energy. So a mouse can't just turn into a horse. It's impossible. There's no path for that to happen because the horse is a bigger system with a lot more energy in it. Okay? So that couldn't happen. You know, could a mouse turn into a mouse of exactly the same, you know, kind of energy size, you know, or some other creature? Not very likely. You could probably prove that couldn't happen, but okay, it starts to become the realm of possibility because there is this quantum jumping. It's just super unlikely. All the molecules would jump into that other state. In fact, you could calculate the likelihood of things like that and find out that, well, in the whole age of the universe, you know, so far, it wouldn't happen. Okay, but the issue with cause and effect is not the randomness because it's bound. The issue is that multiple causes lead to multiple effects, and because of the discrete nature of energy transfer, you don't get to track that. Yes, there's some sort of track through it, some weird kind of track that can ensure patterns like conservation of energy are maintained, but you can't see which of the causes is the cause of the effect. It doesn't work like that. If you want to say there's a single cause, then it's the whole universe, the whole state of the universe at a given moment. You want to say the effect, it's the whole state of the universe, you know, after the moment. All right, but it's a little easier to say, no, there's multiple effects and multiple causes, and there's a gate, this discrete gate that makes it such that this multiplicity is really true, and you cannot trace one-to-one these causes and effects. And I'll give you a very simple thought experiment in classical atomic physics. When, you know, when an atom emits photons, why is it? It's because it has